But again, basically what we want to think of, hey, this is a way of multiplying two vectors. We saw adding and subtracting. So the dot product produces a scalar. All right. We'll contrast that with the cross product. Again, we'll do that one on Thursday, which produces a vector when you multiply the two of them together. We'll talk a little bit more about it on Thursday once we've seen cross product, but they have different uses. They're used in different situations. But one of the things I'll tell you about the dot product is it works for n-dimensional vectors. So it is scalable. So we're going to do it with 2D vectors. We might do it with 3D vectors, but we could do it with a 10-dimensional vector. The cross product only works with 3D vectors, all right? And it has some very interesting properties, which we'll talk about on Thursday. So we're going to start off with a little bit of a context, just to kind of start to get the idea of dot product. And so imagine somebody pulling a wagon, and they're going to pull with 2 pounds of force and move the wagon 1 foot. So that's going to allow us to determine the work done to move the wagon. And now this is going back to the physics definition of work, which you likely saw in Calc 2 as well, which is just the force times the displacement. Okay. Now, the work done to move this wagon is going to be different depending on what angle we pull the wagon at. So first off, very basic scenario. Let's just say the force vector is 2 I-pounds and the distance vector is 1 I. Okay. So we're basically pulling this thing directly horizontal. Well, that's going to give us 2 foot-pounds of work, because we're going to take the component of the force vector in the direction of the distance vector. Well, they're in the same direction. This is just basic multiplication. Where it gets interesting, and this is where we can start to imagine what's going on, right? Imagine that being the handle of the wagon being at a 45-degree angle, right? Well, now the full force is not in the direction of motion, right? You can imagine pulling a wagon, right? The more horizontal you have the handle, the easier it is to pull. So that's what's going on here. So now only the component of the force vector in the direction of motion is counted when we go to multiply work. So only the rad 2I would go towards the work. So in this case, we'd be doing, because the distance will still be 1 foot. In this case, we're only doing rad 2 foot-pounds of work. And it's because we're pulling at that angle instead of keeping it horizontal. You can imagine if we had it at 60 degrees. Now the component in this direction is only 1. And that's what gets multiplied by the displacement. So the reason I use this example is because we can all imagine, or we've all pulled something behind us at some time or another, and we know how that changing the angle changes how hard we have to pull. And so the only thing contributing to moving this thing forward is the component of the force vector that's in the direction of motion. We've talked about vectors and breaking them into components. That's what the dot product does. The dot product looks at the component of one vector in the direction of another vector and multiplies those two together. So that's essentially what the dot product does. So we're going to start off with the geometric definition. I'm going to talk a little bit about this one and where it comes from. So dot product, as you can see, is, we have V dot W. So that little filled in dot means dot product. because we're dealing with vectors. So we know that we're doing multiplication. And it comes up to be the magnitude of V times the magnitude of W times cosine of theta. All right, well, here's what's happening. So let's say we've got two vectors. That'll be V. Uh-oh. You're not moving enough. There we go. I guess we were too still.
Nope. I thought
Perfect.
the light wasn't switched.
Yeah, I know. It didn't count as moving for some reason. And then we got W here. And we got some angle between them. Call it theta. All right. Now, what's happening is we are going to get the component of V. Let's do that in blue. We're going to get the component of V, right? That V1 component that's in the same direction as W, right? So all this is right angle trig. So that V1, well, it's the adjacent side. V is our hypotenuse. So V1 equals V times cosine of theta. It's one of the great things about vectors is it all ends up just being being right angle trig. Let's try that theta again. So magnitude of V would give us the magnitude of V1. So what we're trying to do is multiply V1 times W. So that's what the dot product is. Well, we know V1 is V cosine theta. So subbing that in, there's our V W cosine theta. All right, so that's where the geometric formula comes from. The geometric formula is good if you know the vectors and the angle between them. Okay. 2D, that's really not going to be a big issue. It's easy to find an angle between two vectors. 3D gets a little bit harder. Any dimension above that, what does it mean to have an angle between two vectors that we can't represent geometrically, right? So the geometric definition, it has some uses, but it's a little limited, right? And we'll talk about one of the uses as we look at the other definition. Okay, now we also have an algebraic definition. The algebraic definition is very easy to use. Remember, dot product results in a scalar. So all you have to do for the algebraic definition is multiply the corresponding components of your vector and add them up, and you get a scalar. Again, very easy to use. Involves multiplication. So the dot product with the algebraic definition, as long as we know our vectors, that's what we'll use. Now, where the geometric definition can become helpful is, let's say we want to find the angle between two vectors, and we're given the vectors. We can do the geometric definition up to, except for theta, right? And we could do the algebraic definition and set those equal to each other and solve for theta. Right? So that's one of the places where we'll use the geometric definition most often, is to find the angle between two vectors. Because if we know the vectors, we're always just going to use the algebraic one, because that'll give us a value. And we know that the algebraic version is equal to the magnitude of V times the magnitude of W cosine theta. Not sure why I put that line in there, but again, if we know the vectors V and W, well, this is very easy to do. This is easy to do, and this is easy to do. All we have left is to solve for theta. All right. So that's how we'll use it more often than than actually in the forward direction. So we get a scalar. Again, these definitions hold for n dimensions. Obviously, the geometric doesn't make a lot of sense for any dimension over 3, but the algebraic definition would still work. We're not going to show that they're equal, but what you do to show that they're equal is you use basically law of cosines to show that these two versions of the definition are equal to each other. All right, just a few properties of the dot product and then how we would use it. First off, because the dot product involves multiplication, it's commutative, meaning the order does not matter. If you do v times v dot w, it's the same as w dot v. That will not be exactly the same case with cross product. If you have a scalar, you can multiply the scalar by one of the vectors first, then dot product, or multiply by the other one first, then dot product, or dot product, then multiply by the scalar. All these are pretty basic algebraic properties. There's also a distributive property here at number 3 for our dot product. Okay. Now, this is going to be a big one, and we are going to see this a lot. If two vectors are perpendicular, or you'll also hear the term orthogonal, or you'll also hear the term normal. If they form a 90-degree angle, then their dot product is 0. Right? That's going to be really useful for us going forward. Remember, the geometric definition involves cosine. Cosine of a 90-degree angle is 0. In other words, there is no component of this vector in the direction of a perpendicular vector. Okay. There's just the last one is just a relationship between the magnitude and the dot product. If you dot a vector with itself, it's basically what you're doing is summing up the squares of its components, which is the part that's under the radical in the magnitude. That's not something we use that often. It's just a nice little property. All right. Guys, we're going to deal a lot with what are called normal vectors in here. Again, normal vectors means a vector that is perpendicular to something that we're looking at. So in this case, we want to find a vector perpendicular to the line 4x plus 3y equals 24. We are looking for what's called its normal vector. All right. Now, I'm going to kind of walk you through this on this one. This is going to be something that's going to be very useful to us, though. First off, I'm just going to grab a couple points that are on this line. 0, 8 and 6, 0 are on this line. Now, why would I do that? Well, because then I can find a vector that is between those 2 points. All right. So 6, -8 is a vector that is parallel to this line. Everybody okay with that? Now, what you're going to see when we're done, you're going to have a very quick way of getting the normal vector when a line is in this general form. All right. Now, so what we're looking for is a vector that is perpendicular to 6, -8. So we want a vector that when dotted with 6, -8 comes out to be 0. Now there's an infinite amount of vectors that we could come up with that could do that. You know, I could give you a component to multiply by 6. You could give me a component to multiply by 8 so that it adds to 0, right? That's all that's really happening. But there's one in particular that I picked, and you're going to see really quickly why I picked it. For example, if we do the vector 4, 3, and we run the dot product, right? So let's just kind of review our definition of dot product. That would be 4 times 6 plus 3 times -8. So I've got a positive 24 and a negative 24, and that equals 0. So therefore they are perpendicular, right? Nothing crazy going on there. But what do we like about that vector 4, 3 in relation to the original line? Yeah. We got the 4 right there and the 3 right there. That is not a coincidence. When a line in 2D or 3D, we're going to see on Thursday, is in this general form, AX plus BY equals C. The normal vector is just the vector of those coefficients. We're guaranteed it, and we can always show it by this exact same method. So this is something that generalizes. And this is going to be something very useful to us because anytime we have a line in general form in 2D or 3D, we'll be able to get the normal vector very, very quickly without even having to do any work. We literally just collect the coefficients. So this guy here is what's known as the normal vector. All right, so that's one of the things we'll be looking at today is finding a normal vector showing that something is normal or perpendicular or orthogonal. And again, if you've got a line already in general form, it is as easy as saying, okay, all I got to do is take my coefficients of X and Y. Those are the components of my vector. Vector projections. This is another big use of dot product. The way I like to think of vector projections, you're looking at the influence of one vector in the direction of another one. The example I always give is wind on the path of a plane, because we did a little bit of that on Thursday last week. And so the way I like to think about it is, okay, if we have, let's say we have a plane vector in green here, and then we have another wind vector, and we have another vector for our wind in blue. Okay, so the blue is our wind here. If we want to know how much influence the wind vector is having in the direction of the plane, what we need is the component of the wind vector that's in the direction of the plane. So we would essentially break W into 2 components, one of them being, that would be our W1 that's in the direction of the plane, and then it would have some perpendicular component over here, call it W2, that's perpendicular to the direction of the plane, so it has no influence on the motion of the plane. So what a vector projection does is it does that for us. It finds, the influence of the wind vector in the direction of a plane. So that's the way that I've always conceptualized about what a vector projection does. Another example of the vector projection was the wagon we were talking about earlier. We did a vector projection of the force vector in the direction we were pulling the wagon, because we only cared about the component of the vector that was in our direction of motion. All right. Now, the nice thing is the dot product does this for us. So really what I would do here, if let's give that, if this is our plane vector here, I would make the plane vector a unit vector. So, we got our plane vector, we make it a unit vector. So that would preserve the direction of the plane. And then we just dot that with the wind vector. That's a vector. This guy here, and you'll see it on the next slide. This is a vector projection. What that would do is give us how much of the wind is in the direction of the plane. So we could say, okay, this is how much how much speed the wind is adding to the plane's path.
Or if the wind was blowing the other way, it would be how much.
Yep,
The wind is
taking
reduced.
away. Yep. Okay, so a vector projection, again, just finds the component of the vector that's in the direction of interest. And really the only thing it's a dot product, but you got to make sure that you turn the direction that you're interested in into a dot product, because you want to preserve the direction but get rid of the magnitude. Okay, so if you're doing a vector projection, in this case, I was talking about the wind in the direction of the plane. I need to make sure I turn the plane into a unit vector, because I only want to know the magnitude of the wind component, not what's going on with the plane. Now, we talked a little bit about this. So the vector projection takes care of finding V parallel. V perpendicular is the component that would be doing nothing in the direction of motion because it's perpendicular. If you ever needed to find V perpendicular, well, remember, the two components, V perpendicular and V parallel, have to add up to V. All right, so V perpendicular plus V parallel have to add up to V. So we get V parallel by doing the vector projection. We know V because it was given to us, so we can always find V perpendicular by doing subtraction. There's not a whole lot of instances where we're going to need V parallel, but I have it on here, so I figured I just mention what it's talking about, what it's referring to.
Dr. Clark, can you hear me?
Okay. Oh, there's a little symbol missing here. There should be a dot there for a dot product. I use the A dot U here. So this is just showing how the two notations are the same. What's happening, and I want to make sure I clarify this. What's going on is, if you notice what's happening right here, that's the A dot U. Oh, that's the A dot U from the previous slide. All right, that's that scalar that the dot product gives us, that vector projection. Now what's happening here, multiplying by this, it's getting multiplied by the unit vector again, which is turning that scalar back into a vector. All right, so it depends on what it is we're looking for. Do we just need the scalar? Do we just need the magnitude? Or do we want the answer as a vector? Well, you would multiply by the unit vector one more time. That's where this notation from the video relates to the notation I have in the slide. It's something that's been asked about in the past, because we've turned the plane vector into a unit vector. So what that does, that preserves the direction the plane's heading, but removes its magnitude, so that when we do the dot product, we know what we're getting magnitude-wise is just from the wind. So it isolates that. Makes sense. And then, like we were talking about on that last slide, if you wanted to turn it back into that would be a scalar. If we wanted to turn it back into a vector, we would just multiply by the unit vector of the plane again, which would be multiplying a scalar by a vector, which would turn it back into a vector in that direction. Other questions? Okay, let's go on to the worksheets. Like I said, we're going to do them both at the same time. I'm going to give out 11.3 and 11.4. 11.3 is more done on the computer. So, we might start with 11.4 since we're to work in groups while we're together. And I'm probably going to do number 7 at the end of class. So we're probably going to save, I don't know, maybe 5 to 10 minutes at the end to talk about number 7 on the 11.4 worksheet, because it's a really interesting problem involving the dot product. In the dot product. So what's going on is actually that. All right, so we've got some line coming through the 3x minus 4y. That's line 3x minus 4y. And then we've got some other point out here at 2, 7. And we want to get the shortest distance between that point and the line. Okay, so what we're basically looking for. Well, let me ask you guys. What can we say, if I were to draw the shortest possible line from that point to the line, what would we know about that line I'm about to draw? Yes, so that would represent the shortest distance. Okay, now let's think about what we talked about today. We want something that is perpendicular to this line. Notice it's in its general form, sorry, f equals 20. But what did we talk about today that we know would be perpendicular to this line?
The negative 4x, 3y. Swapping them.
We could do that if we wanted to create another line, but all we need is the direction.
3i minus 4j.
Yeah, what's that called? 3i minus 4j, called the.
Unit.
All right, so it's the first time we talked about it. This thing has what's called a normal vector of 3, negative 4, or 3i minus 4j. And we know that that vector is perpendicular to our line. So I know that the direction of this vector, now this may not be 100% the representation of that vector, but that's going to be the direction of this vector 3, negative 4. Because we know that it is normal to our line. So what we know now is we want to move in a direction from 2, 7 to the line parallel to the normal vector. Okay, great. How are we going to do that? Well, here's where the dot product is going to come in. I'm going to pick a point on the line, and it can be any point. I don't know this point right now. If I did, we'd already be done, right? We could find it, but let's pick something easy. Let's pick this point right here. Because I know that when x is 0, y has to be negative 5. Okay? Now I could have picked any other point. I'm just picking one that I wanted one that was easy. Okay, now here's what we're going to do next. I'm going to find a vector that goes from 2, 7 to 0, negative 5. Again, something we know how to do. So that vector is going to be negative 5 minus 7. So it's going to have a j component of negative 12. So you can see it's very steep. And 0 minus 2. All right. Cool. Everybody follow me so far?
Yeah.
Okay. And now here, this is where the dot product comes in. Think about what we want. We want this right there. That is the vector component of this vector we just found in the direction of the normal vector. So if we call this guy V and this guy N, we want the vector projection of V in the direction of N. That's what the dot product does. So what we need is V dotted with the normal vector that is in the direction of N. Does that make sense? Again, I wanted to do this one with you guys because I don't think it's obvious how the dot product fits in initially. There's other ways of doing this problem using the distance formula and calculus. But this is a very, very slick way with what we were just talking about today. And again, we know everything now. We know V. We know N. right there. We know how to do a vector projection, so we can finish this thing off. Questions about this one? Now, I know I didn't quite finish it, but I got us, I got us far enough that I think you guys could do it, which is what I wanted. And I want to point a couple things out to just kind of bring home dot product. This here is going to give me a scalar, right? So what it's given me is literally it's going to give me this distance right here. So it'll actually give me the magnitude of that vector. Now, like I was talking before, if I were to do this, and this is from the video that you guys watched for today. What that does is that turns it back into a vector, which would be the components for this vector right here. That goes from that point to the line. Now, that's not what we were asked for. We were asked for the magnitude of it. So we were done right here. Call that D. But I just wanted to really bring home that notation that you saw in the video and how it matches up with the way we've been using the dot product. Questions about that?